hopefully in Chem 200, you guys did cover concentration conversion. If you sort of skim through it, then you guys covered that in 152 as well. So let's take a look at this. And again, I want to get started on this and at least complete it next time. So I'm just going to point out the high points. And that high points is that whenever you have a solution, okay, remember, solution in general will always have two components, the solute and the solvent. Together, they form the solution. The solute is basically the minor component. The solvent is the major component. The solute is what is going to be dissolved in the solvent. So it seems to be a simple phenomena, but sometimes you forget based on the fact that it's so simple. Okay, but keep that in mind. There's a solute, the minor component, there's the solvent, the major component, and together they make up the solution. Usually what you want to know is their concentration. That is, how much of the solute do you have in that solution? Remember, the solution is both components together. So whenever you're preparing a solution with a known concentration, you're going to know the solute, you're going to know the solvent, and of course what you get is the solution together. Make sure you know the distinction between these different phrases, okay? Of course, we're not limited to a solid and a liquid. You have different types of solution. You can have a gas in a gas, which we have air. You can have a solid in a solid, in which we have 14 karat gold. 24 karat gold is pure gold. We measure the purity of the gold in jewelry, for example, in carat, not with a C, but with a K. Okay, carat in C is the size of diamonds. Carat with a K is the purity of gold. When you have 24 karat gold, then you have pure gold. If your fiance gives you 12 karat gold, then they're being cheap. It's only 50% gold. Okay. You can also have a liquid in a liquid, in which we have alcoholic beverage, ethanol, and water. So these are different solutions that we have. In this class, we're going to be spending most of our time solid in a liquid or gas in a liquid or gas in a gas. Okay. But again, I want to explain to you that we have different solutions. Now, this is a problem that you guys may have covered in Chem 200 or 152. You're trying to form a 0.10 molar solution. You've got copper, sulfate. When you see this pentahydrate terminology, I want to remind you that the copper sulfate ionic substance have attached to it 5 waters. For every 1 copper sulfate ionic substance, there's 5 waters adhering to it. That's part of the chemical. The molar mass is based on this formula. This dot is not a multiplication sign. It's a plus sign. Okay, copper sulfate and then 5 water molecules sort of attached to it through intermolecular force. When you isolate the copper sulfate crystal, for every 1 copper sulfate, there's 5 waters attached. So when you're trying to figure out the molar mass of this compound, because it's this compound, you got to take the copper, the sulfur, the oxygen, and the water. There's 5 waters, there's 4 oxygen, there's 1 sulfur, and there's 1 copper. CuSO4, 5 waters. And that'll get you the molar mass. And this guy will have a molar mass of about 250 grams per mole. You can try that. So I know that as beginning chemistry students, you might be puzzled about the hydrate. Well, the hydrate is part of the formula. Of course, when you heat it up, then this water molecule will be detached because the intermolecular forces that's holding this water to the copper sulfate will be too much. And what you get now is just copper sulfate. So what you have now is you got copper sulfate is what we call hygroscopic because it picks up moisture from the atmosphere. In order to make it anhydrous, that is lacking water, We heat it up, and now we have copper sulfate. And that has a different molar mass than copper sulfate pentahydrate. Okay. So anyway, these chemicals, because we've got it stored in the shelf, it's picked up water, ambient water, it's copper sulfate pentahydrate, and we want to make a 0.10 molar solution of that compound. Well, it's easy enough to figure it out. How much copper do we need? You guys hopefully remember this from your dimensional analysis. We remember that 0.10 molar is 0.01 moles per liter. We want to form a 1 liter solution. So we want to multiply this by 1 liter. Again, this is dimensional analysis. Then we use the molar mass of copper sulfate. It's 250.0 grams per mole. The moles will cancel, the liters will cancel, and now we can figure out what mass of copper sulfate we need in order to put in a 1 liter volumetric flask so that our solution is 0.10 molar. Okay? Dimensional analysis is always your friend in chemistry. Make sure you remember how to use that. So that's the calculation that you guys would use in this particular case. And we use 250 grams per mole because the chemical is copper sulfate pentahydrate. If it was pure copper sulfate, then that's not the pure molar mass that we would need. So let me clear this real quick and show you that. It's basically what we just got. You get 25 grams, but you could have done this in the top of your head because the concentration that you want is 1/10 of the 1 molar solution. If you wanted to prepare 1 molar solution, then you would have to weigh 250 grams of copper sulfate pentahydrate. The fact that you only want 1/10 of a molar solution, you weigh 1/10 of its molar mass. Anyway, all of this just describes to you what you need to do to prepare this solution. Okay. Let's see how the economy is going. They should be happy with lab gown sapphire. Okay. Here's what I wanted to get to before the end of class. There's 5 ways of expressing concentration. You guys already know molarity. That's moles of solute over liters of solution. Remember, that's liters of solution. That means that you can't just measure the solvent. You have to measure the solvent and the solute together. And the aggregate volume is what you put down there. It's not moles of solute over liters of solvent. It's liters of solution. It contains both. So that's molarity. So we know that. The other unit that you guys are expected to know is molality. Look at the difference. Molarity is with an R. Molality is with an L. Its abbreviation is small m, not capital M. And this is moles of solute, just like molarity, but instead of liters of solution, it's kilograms. It's the mass of the water, solvent. It's the mass of the water. So if you have a solution, you have to pull from that solution just the solvent part in order to get the kilograms of solvent. Okay? And usually you can do that because the numerator will tell you how much solute you have. And so you can subtract that from the total solution in order to get the solvent component. Okay, so that's molality. There's concentration by parts. I like to call this concentration by parts because it's the mass of the solute over the mass of the solution. It's the part of the solute over the total solution. So concentration by parts, if it's a percent by mass, it's the mass of the solute over the mass of the solution. If it's mass volume, then it's the mass of the solute over the volume of the solution. The bottom is always the solution together. It's part over the whole. And if you multiply that by 100, that ratio by 100, then it's a percent. If you multiply it by 1,000,000, however, then it's what we call parts per million. We'll talk about that shortly. So that's concentration by parts right there. And then there's mole fraction. Mole fraction is just the fraction of that particular solute in that solution. So it's the moles of the solute over the total moles in the solution. If we have an aqueous solution, then you need to know the moles of the water and then the moles of the solute. Together, they can make up the moles of the solution. And then there's normality. Maybe normality is new to you, but it's not a difficult phenomenon because normality is actually an easy unit to remember, easy concentration to remember because it's related to molarity. If you know how to calculate molarity, there's one simple conversion factor that you need to convert molarity to normality or vice versa. Okay, so let's take a look at the way we can convert from one unit to the other. This is information about the solute. Usually information about solute, you're either given the mass, and if you know the formula, you can figure out the moles. If you're given the moles and you know the chemical formula, you can figure out the mass. Those are the two information you can pull out from the solute, the minor component. In the solvent, you generally are given, you can get three information. You can get the mass, the moles, and the volume. And you need to know the volume in terms of the density. Here, we have the mass, the moles, but the volume's calculated right here, okay? But together, these two information gives you the solution, and then you can calculate any type of concentration that you want. For example, percent mass, the mass of the solute, the mass of the solvent, together you can, with that information, you can get percent concentration. Molality, you can get the moles of the solute and the mass of the solvent, and you get the molality. Mole fraction, you get the moles of the solute, the moles of the solvent, and you can get the mole fraction. Remember that the total moles of the solution is the moles of the solute and the moles of the solvent together. And then molarity, which is down here, you need the moles of the solute, but you need to take the volume of the solution. In order to get the volume of the solution, you take the mass of the solute, the mass of the solvent, the total mass, and then you use the density of that solution. Remember what density is? It tells you the mass per unit volume. Use the density to calculate the volume of the solution. Now the moles of the solute and the volume of the solution will give you the molarity. And in order to get from molarity to normality, you need to know the definition of equivalence. Equivalence depends on the chemical formula of the compound. We'll talk about that shortly. But it looks simple. You need to practice this in order to actually work out these problems. Okay, so here it is again in the flow chart. You guys can look over this at your leisure. Okay, here's a typical example. We have 3.5 grams of cobalt chloride. Remember, this is cobalt chloride. There's no water involved. This is the anhydrous form. Later in lab, you guys are going to be working with cobalt chloride dihydrate. That means there's two waters. That would have a different molar mass than cobalt chloride. This is the anhydrous form. It has a molar mass of 129.93 grams per mole. Okay, and you want to dissolve it in 100 milliliter solution. Remember, 100 milliliter solution means that both the solute and the solvent together are in 100 milliliters. It's not just a pure solvent in 100 milliliters. It's the solute and the solvent together that is 100 milliliters. And you assume a density of 0.95 grams per milliliters for that solution. What is the molality concentration of the solution? From this description, you guys should also be able to calculate the molarity, the mole fraction, the percent mass, the normality. Okay, but let's just take a look at the molality real quick. Here's how you would calculate the molarity. You take 3.5 grams and you use the molar mass, grams per mole, to get the moles of the cobalt chloride. That's 0.027 moles. Then you can figure out, if you've got a 100 milliliter solution and you want to know say the amount of water in that 100 milliliters. Remember, the solution is the solute and the solvent. Then you have to subtract off the amount of solute in that 100 milliliters. And so that's what we have right here. The mass of the water is going to be 100 milliliters times the density of that solution. That's what we're using right here. That'll give us the mass of the solution. This calculating gives you the mass of the solution. You subtract off the amount of cobalt chloride, and so that is the mass of the water. That mass in water is 0.0915 kilograms. So our molality is just going to be 0.027 moles over 0.0915 kilograms. And that's basically what we have right here. We have a molal solution of 0.294. We're using two significant figures because that's what our data contains. It's 0.29 molal. So that's how you would calculate that. That's how you get a molality. Again, you're just using the fundamentals that you guys have learned. Okay. I want to talk a little bit about percent by mass, and then we'll stop there and then we'll continue next time. Whenever you get a percent concentration, it's the solute over the solution. And you can express that by mass over mass, or weight over weight, mass over volume, or weight over volume, or volume over volume. You have to be told what ratio, and they usually say, by what is the percent concentration by mass? That would be this. What is the percent concentration by volume? That would be this. What is the percent concentration mass volume? That would be this. So you have to be given information as to what type of concentration you need. Anyway, you see the formulas that you use. The units are going to be these. But when you multiply by 100, that's where you get the percent sign. Now, suppose you don't multiply by 100, but you multiply it by 1,000,000. Then that's not parts per 100 anymore. It's actually parts per million. If you multiply by 1,000,000,000, it's actually parts per billion. So you see, calculating parts per million, parts per billion is no different than calculating percent. You just use a different multiplier. Okay, you just use a different multiplier. I think in your activity 1 in lab, you are asked to calculate ppm and ppb. It's not so different than percent. So here's a calculation. You have, let's go with this one. You have 1 drop of alcohol in 1 liter. What is the parts per million concentration? Well, 1 drop is about 0.050 milliliters. If you have 0.050 milliliters and 1 liter is 1,000, and if you want, the solution is going to contain that alcohol as well, and you do this and multiply by 100, what you get is the percent alcohol in that concentration. What you will find is that it's very, very small. It's only 0.005%. But now, instead of multiplying by 100, we multiply by 1,000,000, then it becomes 50 parts per million. The reason why we express things in ppm and ppb is because we want to make sure that the public is aware that that concentration is significant. If you just pass off the concentration as 0.005, people will ignore it because they think it's too minute. On the other hand, if you pass the concentration off as 50 ppm, then it'll take notice, because 50 ppm, 50 looks bigger than 0.005, even though they are the same. Even though they are the same, because the units tell you they are the same. That's why we use ppm and ppb. Okay. Let me stop there because that's a good ending point in terms of what to cover. But I know I've gone pretty fast in these things. Look over the Zoom notes. I'll post it probably when I get to it sometime tomorrow. But we'll cover this in more details on Monday, because you really need to understand how to do the different concentration conversions. For those of you in lab, we'll go over the finer points in the calculations in lab. Okay, for those of you who are not in my lab, you can still go to my website and look at, or go to my Zoom playlist and see how some of these calculations are done. I had to rush through this because I really want to get into kinetics, but usually I won't be going this fast. I know it seems like I'm going really fast, but again, keep in mind this was supposed to be a review. You guys should have already covered it in 152 or 200. So hopefully what I'm telling you is just reinforcing those things that you already learned. And then I really want to use a lot of the end of class session, like after 6 o'clock, in terms of doing group work. We didn't have time to do it today, but on Monday, I do want to spend some time on you guys working together and then turning in something so you can get credit. Okay, and that'd be added on for the participation points. But I want you guys to help each other out if some of these concepts are still vague. Okay, if a lot of these things are too fast, hopefully you took notes and wrote down as we were going over these things questions of concern. That way I can help address that and make sure that you guys are clear on that. Okay, but that's really all that I wanted to say today. And then next time we'll finish up chapter 13, do some group work, and then hopefully hit kinetics. Okay, because the semester will go fast. Anyway, if there's no questions, and I don't see any questions in the chat, I see a bunch of questions earlier that I think I addressed, except for that last one, how the economy is going. They should be happy with lab gowns, sapphires. Okay. Well, I don't know what to say about that. But anyway, hopefully the economy will turn around because of science, because of the fact that there are companies out there, and you guys could be working with these companies in like 5-6 years after you graduate to make some great discoveries. Okay, but with the vaccine out there, I think they're going to get to the people who are going into education, like teachers and hopefully students, by summer. Hopefully, cross our fingers. But if there's no other questions, thanks for attending. For those of you in lab, we start at 6:45, and then we'll continue on with this. Before you leave, what are the things that needs to be turned in before the next class period? Nothing really for the next class period. Remember that by, I believe, February 16th, you do have a syllabus quiz, but really nothing. Go to the homework though, because if you go to homework in My Lab and Mastering, there's a couple of assignments in there that you should be working on in order to, and those aren't due until like the 14th or so. Okay. The quiz is extra credit, right? The syllabus quiz is not extra credit. Okay. It's part of your requirement. But there will be other information there that are extra credit. Okay. So go to Canvas and look in the module, and there are certain questions. Yeah, the Chem 200 pre-quiz is extra credit. Those things that are not really part of the main course, those are extra credit points. So take advantage of that. Okay. So if you have particular questions, go ahead and email me, and I'll try and make sure I should be okay. Email me if you have any questions about those things. I've basically gone to my full course and transferred it, and I looked at some of the links, but there's a bunch of links that are dead. So I need to upgrade that. If you find any dead links, please let me know so I can update it, because I don't want you guys to just go off into the ether, the cloud, and not find it. But you guys have a good weekend. If you're not in my lab, for those of you in lab, we will see you at 6:45. Okay, this is concentration by parts. It's the ratio of the solute over the solution. If you have weight per weight, then it's concentration by mass. If you have weight by volume, then they generally differentiate that by saying M colon V, or M/V, or W instead of using M. Okay, this is V over V, volume over volume. So you notice the units. The units have to be consistent with each other. You can also do kilograms over kilograms if you want, as long as those units cancel out. Okay, you don't have to convert it to grams. You can do kilograms over liters, because that's a relationship right there. But these are the common units. And notice the multiplier. The multiplier will give you the percent. Now, of course, if you change the multiplier to a million, then that gives you parts per million. And that's all you do, really. There's nothing new in that conversion. You just have to recognize that the multiplier makes the unit, okay? And if you multiply by a billion, then it's parts per billion. You can also multiply by a trillion, which is 1 times 10 to the 12th, and you have parts per trillion. And of course, we do that so that a very, very small concentration is significant when we write it down. The units tells you the magnitude. So this is interesting, because if you ever eat any sushi or sashimi like me, where there's a lot of tuna involved, then you guys know that tuna absorbs a lot of mercury, and there's a lot of mercury in the ocean. Okay, and so how do we calculate the amount of mercury in fish? Well, we calculate it by parts per million. So I thought this was sort of interesting in that it tells you, oops, sorry about that, that can white albacore, there's about 32 parts per million in a can. If you can go to a safer, which is 0.12 parts per million for canned light. So you can see that tuna has a lot of mercury. If you go with salmon, that's probably the best thing. Hardly any mercury trace on that. So right here, it kind of tells you, again, they quote things in parts per million, because if they did it by percent, it'll be so small that you might just dismiss it. Okay, let's see why let me see if I can't erase. Okay, oops, trying to erase my, okay. Okay, so again, if you have very, very low concentrations, then they'll do it in terms of parts per million. Let's take I think we did this last time. Again, just examples of how to do these types of calculations. You have 3.5 grams of copper sulfate dissolved in 100 milliliters of solution. Assume that the net density is 1. Whenever you see that, a density of 1, or you don't see a density, you need to make an assumption. If you don't see a density, then just write down, I'm assuming the density of the solution is 1. Of course, if the concentration is very high, that is probably very untrue. If the concentration of the solute is very low, then for the most part, the density of the solution, because it's mostly solvent, is equal to the density of water, which generally is 1 at 20 degrees. Anyway, the density relates the mass of the solution to its volume. You can use that as a conversion factor. So in this particular example, we have 3.5 grams of copper sulfate dissolved in 100 milliliters of solution. Remember that the solution contains the copper sulfate and the water. If the density is 1, then you can assume that the mass of the solution is 100 grams as well, okay? Because the units of density is grams per mil. So a density of 1 means that the grams equals the milliliters. So it's pretty easy in order to figure out the percent, because you have 3.5 grams of copper sulfate in 100 grams of solution. Remember that even though you're given 100 milliliters, you have the density so that you can convert that to the mass of the solution. And what you have here is 3.5 m per m, 3.5% mass per mass. So that's pretty easy, but I want you to understand that these calculations are really not that difficult. What makes them difficult is you guys working too hard. You're trying to find, you're reaching too deep in trying to figure out how to calculate these. Make sure that you understand the unit and pull out the information on the solute and the solvent, or the solute and the solution from that unit. That's the key. So I think we talked about this as well. If you have 1 drop of alcohol and you add it to 1 liter, what is the concentration? Well, 1 drop, it takes, if you're ever in a lab, okay, this is a word, basically an estimate. We always do this in lab. It takes about 20 drops of liquid to equal 1 milliliter, okay? It takes about 20 drops, rule of thumb. So if you have 1 drop, then it's 1/20th of a milliliter, okay? 1/20th of a milliliter is 0.05 milliliters. And so what is the concentration volume per volume? Then it's going to be 0.05 milliliters over 1,000.05 milliliters. Remember that it's a volume. So this is basically it. Here you can see that even though I don't put 1,000.05, 0.05 is so minute that it's going to be insignificant. So you can just put 0.05 over 1,000. It'll get you the same number, especially since you're using one significant figure. Okay, you've got one significant figure because you've got 1 drop. So you can easily do this, but notice if you multiply it by 100, then that number is 0.005%. In order to make that number stand out, we multiply by 1,000,000 and we get 50 parts per million. 50 parts per million is much more significant than 0.005, although they're the same. Okay, they're the same. Take a look at Canvas. Let me see if I can switch view here, because there is a question on BAC. You guys can look at that and submit that. Let me just change my screen here and do this. Switch screen. Let me go to Canvas so that you guys can see that. So I think you guys see my screen here. So let me go over here under, I think it's under discussion. One of you already submit this. So under the discussion right here, BAC, blood alcohol level, you can open that. Now don't submit anything here. You actually have to go to this link, and then it gives you a description of this particular problem. And the problem is find out the beer information. Okay, find your favorite alcoholic beverage. If you don't consume alcohol, fine. Calculate it for some theoretical person, a friend or someone. That's okay. Okay. My hat's to you. You don't consume alcohol. That's fine. But you can still do this calculation. Okay, so that's your percent ethanol. Ethanol is the only thing that you can drink in your beverage. And then you also need to figure out how much blood your body contains, and it's based on your body mass. So you can go over here and figure out how much blood is in you based on your mass. You need those two information so you can calculate the percent of alcohol when you consume an alcoholic beverage. Okay, so once you do that, these are the directions for that. You can calculate what your BAC is, your blood alcohol content. And if you do that and submit it, and you can submit it because there's going to be a submit button there, do your work on paper, show me the calculation. There's also a blood calculator here, BAC calculator. And all you have to do is put in the information in this calculator, and then it'll calculate based on your body mass and the alcoholic beverage you have, how much blood alcohol you have.
Could you real quick show us how to use this calculator? Because I tried earlier and I couldn't find any kind of link or whatever.
Right. Let's see. Let me yeah, this was there should have been, let's just see. I know this was the, let's see, ohm calculator recipe. Let me go into this and give you some details on this, because this was the link that I have. Sometimes link change over time, and so I don't know if that's the case, but this thing should be, last I check, okay, there should have been a calculator in here that allows you to do that. If not, then I'll find the correct link. I'm sorry about that. Okay. Yeah, there is no link here. I should have checked this to make sure it was up to date. Let's see. Yeah, it doesn't show me a calculation. It only gives you a way in which you can order some alcoholic beverage. Let me change this link, because I know that there was a blood alcohol calculator, and all you do is put in the beverage and then your body mass, and it'll calculate that for you. Okay, so I apologize for that. Let me go back and I'll change that after class, because this thing isn't due until I think it's due on the 15th, which is this coming weekend. Okay, so you can still work on that. Let me go back to our discussion. Thanks for letting me know about that. So let's see. Let's go back to this. Okay. Okay. So this is an example again of just doing a concentration calculation based on percent. Now, I remember you can also do this. You can actually calculate based on your, this right here, the blood alcohol level in California is 0.080%. If you are above that, then you are under the influence, okay? So they could pretty much handcuff you and take you away. So if you have 0.080 and you weigh 160 pounds, okay, in which case you have about approximately 4.7 liters of blood in your system. Well, in this particular case, and you have, if a 160-pound person has 4.7 liters blood and has a BAC of 0.12, calculate the amount of alcohol in their body. And you can do that because if you have 0.12%, then you have 0.12 milliliters in 1,100 milliliters of blood. And if you have 4.7 liters, then that's 4,700 milliliters. And if you do that, then the volume of blood will cancel, and that'll tell you the volume of alcohol. Again, you can see that I am taking this 0.12% and then I'm converting it into useful information, 0.12 over 100. 0.12 over 100 is 0.12%. I'm converting that to useful information so that I can do dimensional analysis. And if you do this math, you will come up with 5.64 milliliters of alcohol in that person. Or if you do the conversion factor, depend of 29.57 milliliters per ounce, you've got 0.191 ounce of alcohol. That's ethanol in your system. So the best way to do these calculations is to understand dimensional analysis. That's what I'm saying. Okay. Of course, if you've got 0.12 blood alcohol in you, then this is what's happening. You have overexpression, emotional swings, you have anger and sadness, you're boisterous, and you have a decrease in the libido. So this is based on your blood alcohol level from the state of California. Okay. This tells you what your blood alcohol level will be depending on your mass, your weight, and the amount of alcoholic beverage you consume. This is an approximation, but that's usually what's given out so that people do not drink and drive. And I was watching Shark Week one time when I was doing the lecture notes for this, and they were claiming, I don't know if it's true, they were claiming that sharks could detect blood a mile away. Okay, I thought that was pretty amazing, but I did the calculation anyway. If you have a mile cube, okay, you have a mile cube, what is that volume? Well, there's 5280 feet in 1 mile, so you can do the conversion, okay, right here. And what you find out is that a mile cube is 4.17 times 10 to the 15 milliliters. You guys can do that. Just remember to remember the conversion factors and do dimensional analysis. So if you've got 1 drop of blood, which is 0.05 milliliters, in 4.17 times 10 to the 15 milliliters of seawater, what is the concentration? Well, it's so small that if we do it in parts per billion, that's 0.00012, no, 0.00. You can see how many zeros we have. 12 parts per billion. Okay, if you multiply by a million, it's still 0.00012 parts per trillion. So I actually went into Google and I found a unit that is significant. It's called a quintillion. So if you multiply by 1 times 10 to the 18th, then, sorry about that, we get, in this particular case, I believe it's going to be 12 parts per quintillion. Again, the units tells you the magnitude in this particular case, okay? So that's what I wanted to show you in this particular example, is that if you have something very small and you want it to stand out, then just multiply it by a big multiplier and then change the unit accordingly, and that'll work. So I'm going to go through this because a lot of this is what we talked about last time, but I do want to break out to this particular problem, okay? So this problem, go ahead and write it down because this is where we're going to break out into break rooms, breakout session. Write down that you have 0.085% dioxin, okay? So the question is, how much dioxin is present? I believe this is 1.5 liters of aqueous solution. So the first part of this problem is to calculate the mass of dioxin in 1.5 liter solution. Solution now. Solution means that you have water and dioxin in there. Okay, this particular example, the molar mass of dioxin, by the way, is 84.07 grams per mole. I give you that information. And the density of this solution is 1.01. So what I'm going to do is I'm going to make sure you write that. I'm going to give you guys about 5-10 minutes. You guys go into a break room and calculate not only the mass of dioxin in 1.5 liter, but also the molality. So everyone should be out of the break room at this point. Let me just double check. Okay, I think everybody's back into the regular classroom. If you guys have a chance, make sure you upload it. Let me just show you what is involved in this problem. A bunch of you got it right, but for those of you who were struggling a little bit, let me kind of assist. First of all, you know, you've got, whenever you see this concentration right here, 0.085%, and it tells you it's by mass. So you want to say it's 0.085 grams dioxin in 100 grams of solution. That's what 0.085% means. If you take 0.085 divided by 100, multiply by 100, you get 0.085%. Okay, so you can use that as a way of getting information about the solute and then the solution. Now you have 1.5 liters of solution, okay? So the question is, what is the mass of that? Because remember, 1.5 liters is a volume and 100 grams is a mass. They're not the same unless the density is 1. So you need to figure out the relationship between the two. And of course, the density gives you that relationship. So let me clear this real quick. Okay, in most stoichiometry problem, the first step is to convert the volume of solution to mass of solution using the mass of dioxin. And then this just tells you the strategy that you want. So 1.5 liters equals 1500 milliliters, and 0.085 equals 0.085 grams per 100 grams. First thing we're going to do is calculate the mass of dioxin by using this density. See how I have milliliters here? Well, this tells me if I stop my calculation here, that'll be the mass of the solution in grams. The mass of the solution, and then I use the concentration. Again, this is through dimensional analysis, and the grams of the solution cancels, and what I have is 1.2878 grams of dioxin. Okay. The difficulty a lot of you will have is that you're going to get confused as to what is the solution, what is the solvent, what is the solute. That's why you have to carry the units and the identifier in order to make sure it's clear in your mind. Once we have the mass of dioxin, then we can use the molar mass to get the moles. Okay, and then remember that we can figure out that the volume of the solution or the mass of the solution is here. If we stop our calculation, if we subtract off the mass of the dioxin, which is 1.2878, then we have the mass of the water. And that's what you see right here. The moles of dioxin is, in this particular case, 0.0153 moles of dioxin. And then what we can do now is we can get the mass of the water. Again, here we're using the density of the solution with the volume of the solution. That'll give you the mass of the solution. And then we're subtracting off the mass of the dioxin. So what we have is 1,513.71 grams of water. It's not 1,500 grams of water because remember, the density is not 1. Now we can convert it to the molality. So you have to be in that frame thought process in order to do these types of problems. And activity number 3, for those of you in lab, you have a bunch of these questions because it's going to require you to calculate percent, molality, and all that. But this is a good practice for that. You can see that once you understand what the components are, the problems are not that difficult. Okay, but it's making sure you understand what the components are: solute, solvent, solution, in order to work out the problem. So let me move along. The rest of these are just more examples of the same. Okay. Here's molarity as well. So you guys can look over this in terms of just review. I give you a bunch of examples here because I want you to see what the thought process are, and that dimensional analysis is key in solving a lot of these problems. Okay, so I won't really do them unless you have questions. Go over them. You might see some of these questions or similar questions in your next quiz. Okay, and really all these types of problems are really nothing more than stoichiometry. This is something I usually give to my beginning course or even my Chem 200 course. It's a stoichiometry map. It relates the concentration to the mass. It relates the concentration to the number of molecules or atoms. It relates the mass to the volume through all these conversion factors. So the key to to being successful in these types of problems is to know your dimensional analysis. Okay, so let me just move along here. You guys can look at this in terms of some of the calculations. I want to next go to this section of the lecture notes. It's dilution. There's several ways of preparing solutions. One is to find the solute, measure it out, put it in a container, and add solvent. Okay, and then depending on the amount of solute and the amount of solvent you have, you can get a concentration. Another way of preparing a solution is by serial dilution, where you have a stock solution. Stock solution is the original solution that you've prepared, and then you do a series of you take an aliquot. An aliquot means a portion. You put it in another container, and then you add water or you add solvent to it. And what happens is that the concentration of that new solution will always be lower than the stock, the original solution. But now you can prepare a series of solution, which you will do a lot in lab, via dilution calculation. This cartoon right here gives you a classic example. The aliquot is a can. Aliquot means portion. Means portion. So the aliquot here is 1 can of orange juice. And the direction says to mix in 1 can of orange juice and then add 3 cans of water. So of course, what you know is that the resulting solution, the resulting mixture is going to be way more dilute than the original, but that's the idea of this particular exercise. And so you're doing a dilution. The amount of solutes in this can is the same as the amount of solutes in your end product. The number of molecules that you originally had before the dilution is equal to the number of molecules that you would have after dilution. The only thing that you're doing is adding more water, adding more solvent, so that per volume you have less. Okay, but the amount of solute before the dilution and the amount of solute after the dilution are equal. The only difference again is that the volume has increased, so you have less in your resulting solution per volume. So that's the whole idea of dilution. Okay, and here you can see, clear it is. Here you can see that I have 1, 2, 3, 4, 5 solute, but when I dilute it, there's still going to be 5 in here, except now it's in a bigger volume. And that's the key to the dilution equation. The dilution equation is this right here. M1V1 equals M2V2. I don't like to limit this equation to molarity. That's what M represents. If you guys learned it in Chem 200. I don't like to limit it to molarity because you can use any type of concentration as long as the concentrations are equal on both sides. This could be percent. This could be molality. This could be mole fraction. Okay, so the idea is that the amount of solute before the dilution is equal to the amount of solute after dilution, because all you're really doing is adding more solvent. You're not taking anything away. You're not adding anything new. So in terms of the solute, it's conserved. Okay. The hardest part of these types of problem is to identify what is the original concentration, what is the original volume. The original volume generally is the aliquot. What is the portion of that stock solution that is used? And then you're generally calculating the new concentration in its new volume. So this is a way of doing a shortcut. C1V1 equals C2V2, okay? And in this particular case, suppose you have 10 mils of 3.4 times 10 to minus 2 molar of nitric acid, and it's diluted to 50 milliliters. So right away, you should be able to say that I have 10 mils here. That's what you have, because that's the portion that is used. You've got 3.4 times 10 to the minus 2 molar of nitric acid. And then your new volume is 50 milliliters. So you can just plug it in and then you can calculate that new concentration, which is right here. Okay, that new concentration is going to be lower than the original, and it comes out to be 6.8 times 10 to the minus 3. These calculations are not difficult if you remember these equations, but you need to practice it to be comfortable with them. You can also use, instead of molarity, percent mass or percent volume per volume. That's the versatility of these of this equation. You don't have to limit it to molarity, okay? Because what happens is that the units will cancel, or the units will get you the appropriate unit when you do the calculation. You've got to make sure, however, that these two have the same units and these two have the same unit. If you don't have the same unit, then your calculation is going to be messed up, okay? This only works when the units on both sides of the equations are the same. So again, this is just another example. There is a bottle of 0.05 molar sucrose stock solution. So that's your original concentration. That's C1. Give precise direction to your assistants to prepare 250 mils. To prepare, that means that that's the final volume of a 0.348 molar solution. So in this particular case, that's the concentration that you are shooting for. That's C2. So what you need to do is you need to figure out what aliquot do you need in order to put into a 250 volumetric flask and then fill the flask to the 250 milliliter mark with solvent. Okay, so in this problem, what you're looking for is V1. And let's see. So try and solve that, and you should be able to calculate it. I think, yeah. You can easily do the math in that particular problem. Try and solve that. So this is another example of concentration. You've got 10 grams of manganese sulfate monohydrate. That's monohydrate, meaning it has one water. It's placed in a 1 liter volumetric flask and filled to the mark with water. Okay. What volume is necessary to prepare 250 mils of 0.05% solution? So this is, again, you've got the final volume, you've got the final concentration. What you need to do is you need to figure out what is your initial concentration, so you can figure out what aliquot you need in order to prepare that second solution. Now you've got 10.0 grams. Remember the concentration we have is 0.05. So you've got 10.0 grams in 1,000 milliliters. I can assume in this particular case that the density is 1. So that is 1,000 grams. And if I multiply that by 100, I've got my percent concentration of manganese sulfate, which is going to be C1. So you basically would just have to do that to calculate C1. Now you know what C2 is going to be. You know what V2 is going to be. You need to determine how much, what aliquot to put in a, let's see, 250 ml vol flask, because that's what's given. You need a 250 ml vol flask. And then fill to the mark with water so that the final concentration is 0.05%. So that's what this problem is. You guys are going to need to know how to do this, especially for lab. Okay, this is actually, if you take a look right here, it's actually a 1% solution. Okay, 10 over 1,000 times 100. This is actually, because the density is 1, 1,000 milliliters is 1,000 grams, so it's 1%. You can do this for your math. You can calculate again the volume that is necessary, and the volume that is necessary is 12.5 mils. Okay, so the rest of this lecture notes just gives you more examples of concentration conversions. Please practice that. Chapter 13 should have been a review. If it's new to you, then practice these problems. Okay, practice these problems so you are at second nature, because you do a lot of concentration conversions in this class. That's why we spend time on that. Okay.